All right, let's dive into one of the biggest detective stories in human history. We're going to unravel a mystery that took thousands of years to solve, a quest to answer one of the most fundamental questions you can possibly ask.
I mean, really think about it. What are you made of? What about the chair you're sitting on? The air you're breathing right now? For literally millennia, humans have been asking this, trying to look past the surface of things to understand what the universe is actually built from.
And what's wild is that people from completely different parts of the world came to a similar conclusion. Way back around 500 BC, an Indian philosopher, Maharishi Kanad, suggested that everything was made of these tiny, unbreakable bits he called parmanu. And get this, around the very same time, over in Greece, Democritus had the same basic idea, calling his particles atoms. No internet, no phones, just two brilliant minds arriving at the same profound insight. But, for the next 2,000 years, that's all it was, a really cool idea, a philosophy. There was just no way to prove it, so the mystery just sat there, waiting for the tools of science to finally catch up.
And then, boom, in the late 18th century, everything started to change. Scientists like Antoine Lavoisier finally had the gear to run super precise experiments, and they started finding the first real clues, these unbreakable rules that matter just seemed to follow no matter what.
So, the first big clue sounds a little technical, the law of conservation of mass. But honestly, the idea is super simple. It just means that if you have a closed container, the total amount of stuff you start with is exactly the same as the amount of stuff you end up with. Nothing just vanishes, and nothing appears out of thin air. And the way they proved this was so clever and simple. They'd seal two different chemicals inside a flask and weigh it. Then, they'd just tip the flask over, let the chemicals mix and react, and then weigh it again. And every single time, the mass was identical. It never changed. This was a huge piece of the puzzle. Now, the second clue was just as strange. Scientists found out that chemical compounds are like incredibly strict recipes. This idea, the law of constant proportions, basically says that a pure substance, like water for instance, is always made of the same elements combined in the exact same ratio by weight. Water is the perfect example. It doesn't matter if you get it from an iceberg in Antarctica, a river in the Amazon, or if you make it in a lab. It will always be made of 1 part hydrogen to 8 parts oxygen by mass. Always. This fixed, unchangeable recipe was a total mystery. So, okay, now we've got these two solid clues. 1, mass never disappears, and 2, compounds have these fixed recipes. But this just led to an even bigger question. Why? What was going on under the hood that was forcing matter to play by these rules? Well, the detective who finally cracked the case was a British chemist named John Dalton. He took these two clues, dusted off that ancient idea of atoms, and forged them into a scientific theory that changed everything. And Dalton's own story is pretty incredible. He was born into a poor family, and get this, he became a teacher when he was just 12 years old. Can you imagine? He was a brilliant, self-taught scientist who, in 1808, completely revolutionized the world of chemistry. So this is the heart of it all, Dalton's atomic theory. He basically said, okay, all matter is made of these tiny particles called atoms. You can't divide them or destroy them. He said every element, like gold or oxygen, has its own unique type of atom, and they're all identical. And here's the kicker. These atoms combine in simple whole number ratios to build everything we see around us. So, did this theory actually explain the clues? Well, let's go back to that first one. The fact that mass is always conserved in a reaction. And here it is, the aha moment. Dalton's explanation was brilliant. He said a chemical reaction isn't creating or destroying matter. It's just rearranging the atoms. You're just shuffling them around into new groups. So if the atoms themselves can't be destroyed, then of course the total mass has to stay the same. Mystery number 1? Solved.
All right, but what about the second clue? Why do compounds like water always have that weirdly specific 1:8 mass ratio? What's going on with that strict recipe?
Dalton's theory nailed this one too. If water is always made by combining a fixed number of hydrogen atoms and oxygen atoms, and each of those atoms has its own specific mass, then the final mass ratio of the whole compound has to be constant. The recipe for the atoms dictates the recipe for the mass. It all just clicked into place.
I mean, this theory was a total game changer. For the first time ever, scientists had a real framework for understanding matter, and that allowed them to create something amazing, a universal language to describe it all. the language of chemical symbols and formulas.
Now, Dalton himself started with these kind of cool but clunky picture-like symbols. But pretty quickly, another scientist named Berzelius said, hey, we can do better. And he proposed the simple, elegant letter-based symbols we still use today. C for carbon, O for oxygen. Much easier, right?
And to predict how all these different atoms would actually combine, chemists developed the idea of valency. You can think of it as the number of arms an atom has to connect with other atoms. So hydrogen has one arm and oxygen has two. It's a great way to picture how they link up. This even led to some really neat little tricks, like the crisscross method for quickly figuring out a chemical formula. You just write down the symbols and their valencies, crisscross the numbers, and boom, you get MgCl2 for magnesium chloride. It turned a complicated rule into a simple, visual shortcut. So when you step back and look at this whole journey, from ancient philosophy to modern science, it all leads to one incredible conclusion. These unimaginably tiny, invisible particles are the building blocks of, well, everything, our entire world.
And just how tiny are we talking? Honestly, the scale's almost impossible to wrap your head around. If an apple is about 1/10 of a meter wide, a single atom of hydrogen is 1/10 billionth of a meter. You could stack millions of them on top of each other, and the stack would still be thinner than a single page of a book.
Just let that number sink in for a second. That's the radius of one single hydrogen atom. It's a scale so small, it's hard for our brains to even process it. And yet, the entire universe is built out of things this small. And this, to me, is the most incredible part of the whole story. For Dalton, atoms were a theory, a brilliant idea. But for us today, they're a visible reality. With modern technology, we can now actually produce images of individual atoms. We can see the fundamental blocks of our universe that ancient philosophers only dreamed about. It really makes you wonder, now that we can finally see them, what other secrets are they still hiding?